In this video, we're going to begin graphing equations. The graph of an equation is just a representation of the solutions to that equation. We're working with equations in two variables, and so we're going to have a two-dimensional graph. For now, we're only going to find these graphs by plotting points and trying to look for a pattern. As you probably know, there are advanced techniques for graphing, and we'll get into some of those later on in the course. For now, we're just going to stick with the most primitive method, which is to plot a bunch of points and then connect them based on their pattern. As a part of that, we'll find x and y intercepts. We'll review what those are and how you find them. And at the end of the lecture, we're going to talk about arrow notation, which may be new to you. For a lot of students at this level, at the college algebra level, this is a concept they haven't run into before, so we'll cover that as well. First, let's start with the general idea behind sketching a graph. The points on the graph of an equation represent the solutions. So if you have an equation in two variables, x and y, then each point x comma y represents a pair of numbers that makes the equation true. So one way to come up with those points is to select an input for one variable and solve for the other variable. Now it is possible that for the equation you're working with, plugging in one number leads to no real solutions for the other, in which case you don't get a point from that. So you want to be kind of choosy about the inputs that you use. Once you've found a solution in terms of x and y, you're going to write an ordered pair with x first and y second, and that's a location that you can plot. We represent that location with a point. Now, depending on the complexity of the graph, you might need to find only 2 points, or you might need to find a bunch of points. It all depends on how long it takes you to see what the pattern is. For really complicated equations, plotting points won't do the job. You'll have to do some advanced techniques. We, of course, won't be looking at any of those in this video. A collection of points you'll definitely want to consider finding are the intercepts. The x-intercept is a point on the x-axis, and a y-intercept is a point on the y-axis. If a point is on the x-axis, then its y-coordinate is 0. So to find x-intercepts, you let y equal 0 and solve for x. If that leads to no solutions, then the graph never touches the x-axis. Similarly, to find y-intercepts, you let x equal 0 and you solve for y. And again, if you get no solutions from that, that means that the graph never touches the y-axis. It is possible for the equation that you create to have no solutions. In that case, you just don't plot a point. You just have to pick another input. Once you've established a pattern and you have a pretty good idea of where the graph turns and what its end behavior is, what it does on the left edge and the right edge, then you can connect the points with a line or a curve when you see what that pattern is. I want to reiterate that this is a primitive way of graphing. This is going to be our fallback method. We're going to build a library of functions where we know basic shapes based on equations, and we're going to learn some other techniques. And then for those of you headed to calculus, you'll learn some even more advanced techniques. But if all else fails, you can just plot a bunch of points and then graph that way. The examples we're going to demonstrate are simple examples so that we don't have to plot a bunch of points. If you have a lot of algebra experience, you might know how to graph these without coming up with the number of points that we're going to draw. I'm just using these as simple examples of this technique. So if you think that we're doing this kind of the long way because there's a better way to find these graphs, you're absolutely right. We are going to learn those better ways later as well. So be patient. The first equation we're going to graph is the equation y equals 2x plus 6. Again, some of you might know a very quick way to graph this. That's awesome. We're going to do this kind of the long way by plotting this point by point. For now. Very soon we're going to cover a faster way to come up with this graph. I strongly recommend for any graph that you have to draw by hand that you try to find the intercepts. Often they're easy to find because the number you plug in is 0. To find the x-intercept, you plug 0 in for y. So we get the equation 0 equals 2x plus 6, and we'll do a little bit of algebra to solve for x. We get that x equals negative 3. We can write that as the ordered pair negative 3 comma 0, or as an alternative to that, you can create a table of values of x and y and write it in there when x is negative 3, y is 0. Let's also find the y-intercept. A y-intercept is a point on the y-axis, and that means that the x value is 0. This will be even easier because we don't have to do any juggling of the symbols. Y equals 2 times 0 plus 6. Of course, anything times 0 is 0, and anything plus 0 is itself, so this is just y equals 6. And again, we could write that as an ordered pair, x first, 0, 6. Or we could write this as an entry in our table, 0 and 6. Again, I know many of you can look at that and tell what the y-intercept is, and you can graph this function without any of this work. But let's play dumb and do this point by point. Give myself some tick marks to work off of. And what have we learned so far? When x is -3, y is 0. So that point would sit on the x-axis. That's why we call it an x-intercept. 3 units to the left of the y-axis. The second point we found 6 units above the origin. 1, 2, 3, 4, 5, 6. Again, I know some of you are screaming at me to just draw the graph now. But if you didn't have any prior knowledge about what the graph of this equation would look like, 2 points isn't really a whole lot to go off of. So you might find a couple more. And what you want to do is choose inputs that will be easy to work with and give you some information. So looking at this equation, it's solved for y. So if I pick a number for x, all I have to do is arithmetic. You saw this when we found the intercept. When we found the y-intercept, that was easy because we plugged a number in for x and we just had to do the arithmetic. Finding the x-intercept wasn't hard, but it did take a little bit of algebra. And as you can imagine, if this equation was more complicated, solving for x could be difficult or even impossible. So typically you want to select inputs for the variable that is not by itself, because then all you have to do is arithmetic to find the value of the other variable. What inputs would I use? Well, I'd probably pick one in between these two and maybe one outside here. So I might plug in -1 as a representative between the two. I might plug in 1, and I might plug in -4, just to give myself a little bit of information. Notice again that all of my choices here are for x, because then all I have to do is arithmetic. I'll do that arithmetic off to the side here. If I plug in -1, I get y equals 2 times -1 plus 6. That's 4. So we get -1, 4. When I plug in +1, I get y equals 2 times +1 plus 6. That's 8. So 1, 8. And when I plug in -4, I get 2 times -4 plus 6. That's -2. And while my graph isn't perfect, there's a pretty obvious pattern here. These seem to be falling in a straight line. Now you might notice that I missed this point pretty badly. The way that you mask that is to just make that point bigger, and then to hide that, you make all of the points bigger, and then nobody knows how terrible your graph was. I want to say one more time that I know exactly 0% of you were shocked that this graph came out to a line, and I know some of you are probably even trying to fight the urge to punch through the screen to hit me for doing it this way. I'm trying to demonstrate the process of plotting points in order to come up with the graph of an equation. Later on in this course, maybe in a future course, you'll run into an equation where you're not as comfortable with what the graph would look like on site, and so one way to handle that is to plot some points. X and y-intercepts are almost always a good idea. You might find some other points as well. And the fact that I know that you've seen this before is bared out because I didn't even bother to fill in the table, because I know you've done this before, but I should have filled in this table. My apologies for not doing that as we did it. Let's just do one more example, and here I'll pick one where maybe you might not know exactly what this looks like. I bet you have an idea, but if your algebra is a little rusty, you might get this one wrong. This one asks us to graph x equals the negation of y squared plus 4. So let's find ourselves some intercepts. To find an x-intercept, you let y equal 0. That winds up being the easier one in this example because x is already solved for. So we get x equals the opposite of 0 squared plus 4, which of course is just 4. So when y is 0, x is 4. Be sure to write this in the correct order. That's the point 4, 0, because x is 4, y is 0. To find the y-intercept, you let x equal 0. And here we'll have to do a little bit of algebra. Put 0 in for x and set that equal to the negation of y squared plus 4. Here I would add y squared to both sides and use extraction of roots. You could also try to factor that right side. And remember, we get two solutions here. We get y equals plus or minus 2. That actually corresponds to 2 points. When x is 0, y could be 2 or -2. If I were making the table, this might be a little clearer. So we had that first point that when x was 4, y was 0. And then we're saying if we plug 2 in for y, we get 0 for x. You can see that. 2 squared is 4, the negation is -4. Add 4 to that, you get 0. And when you plug negative 2 in for y, you also get 0 because negative 2 squared is also 4. The negation of that is negative 4. Add that to 4 and you get 0. Let's plot those 3 points. So we've said that when x is 4, y is 0. That would be on the x-axis, 4 units to the right of the origin. When x is 0, y could either be positive 2 or negative 2. So we get these 2 points here. Again, a lot of people would know what this graph looks like, although I guess that percentage is a lot smaller than the percentage who knew what the first graph looked like. So let's plot a couple more points. We'd want to plug in for y because it's the easier one to work with. So if I let y equal 3 in the equation, I get x equals the negation of 3 squared plus 4. Remember, the order of operations tells us to square first, so that's negative 9 plus 4, which is negative 5. Let me be careful to fill in the table right away. I plugged in 3 for y, and I got negative 5 for x. So when x is negative 5, and I didn't go far enough around here, y is 3. So that's like here. Let me plug in negative 3 for y. Again, choosing negative 3 because it's outside of the bound that we already had here. So x equals the negation of negative 3 squared plus 4. Order of operations, again, I square negative 3 first. I don't do a negative times a negative as a positive first. I square first. So I get the exact same calculation. And you see there's kind of a symmetry to this graph. When y is negative 3, x is again negative 5. So that's a point down below the axis. So it seems like we have a pretty good idea of what this graph looks like on this side. And using a little bit of numerical intuition, the bigger the magnitude of the y value we pick, the larger this negative number is going to be, so this thing's just going to keep extending further and further away, like this. Missed that part by a little bit, missed this part by a little bit. How do I know there aren't going to be any points to the right of x equals 4? Well, I guess we could investigate that by picking a number bigger than 4 for x and doing the algebra. So a quick check here. If I plugged 5 in for x, I get the negation of y squared plus 4 is equal to 5. Subtracting 4 from both sides, I get 1 equals the negation of y squared, which means that y squared equals negative 1. And while that equation has 2 solutions, plus or minus I, those aren't numbers that we can plot on the y-axis. The y-axis is a number line of real numbers. So in other words, there is no point on this graph whose x-coordinate is 5. Of course, that's going to be true for any number bigger than 4 that we plug in for x, because when we subtract here, we're going to get a positive number. Then we divide, that becomes negative, and we're going to wind up with the square root of a negative number. There are no points to the right of 4. So we get this U-shaped graph that we call a parabola. And I would guess many of you knew this was going to be a parabola. However, if you haven't had a lot of graphing experience, you might not have known this was a parabola that opened to the left and that its vertex was at 4, 0. Doing the point-by-point thing kind of helped with that part. So those are some of the nuances of graphing point by point. Again, that might not be the most efficient way to graph some equations, especially simple ones, but at least it's something you can try if you feel stuck. The other thing we're going to do in this lesson is talk about arrow notation. Arrow notation is a shorthand way to describe the behavior of a graph at a certain location. Here I've written 5 different arrow notations that we're going to run into. In these first 3, a is being used as a real number. The first one says x arrow a, and then there's this little superscript minus sign at the top. The way that we read this is x approaches a from the left. So we're asking what happens to the graph as the x values get closer and closer to a from the left side for values that are smaller than a. The second notation says x arrow a, and then there's a little superscript plus sign. We read this as x approaches a from the right. So now we're asking what happens to the graph as we approach a from the high side, from above, values larger than a, the right side of a. The third one is kind of a two-sided issue. This just says x approaches a, so from either side. If there's a common behavior from both sides, then we can talk about what happens as x approaches a. If the behavior is different, then we can't say anything about it because the two behaviors are different, and that's why we have these one-sided options. The last 2 arrow notations are for unbounded values of x. As x approaches infinity, so as x gets arbitrarily large. And the last one as x approaches negative infinity, so as x gets arbitrarily small. The arrow notation is used to indicate behavior of the graph. So you can see we've got this broken graph. This first piece is kind of a parabolic shape that just kind of stops at the point 1, 3. Then there's this kind of jump in the graph. In fact, we call that a jump discontinuity, where the graph has this vertical gap and the graph just kind of starts over at the point 1, 2, and the pattern becomes linear instead of that curved shape pointing downward. We can see that the graph approaches two different locations as x gets closer and closer to 1. It just depends on which side of 1 you're on. The first line that we have here says, as x approaches 1 from the left, y approaches what? We're going to fill that in. Well, if we're approaching 1 from the left, then we're considering points that are smaller than 1. So we're on this branch of the graph, and we're going to get closer and closer to 1 from the left side. Now I know I'm swinging to the right as I do this, but I'm coming in from the left side of 1. And as I come in from the left side of 1, the points on the graph get closer and closer to this location at 1, 3. So the y-coordinate we're getting closer and closer to from the left side of 1 is 3. The second line here asks, as x approaches 1 from the right, what is the behavior of y? Well, if we're approaching 1 from the right, then we're considering values that are bigger than 1. Well, as I come in on this linear branch here, which is to the right of 1, I get closer and closer to this location. I know we don't actually obtain that spot, but that's the whole point of the arrow notation, is to ask what are we getting close to, not where do we land. As we approach 1 from the right, we get closer and closer to this point whose y-coordinate is 2. And so this arrow notation gives us a way to indicate that the behavior on each side of 1 is different. On the left side, we get closer and closer to a y-coordinate of 3, and on the right side, we get closer and closer to a y-coordinate of 2. Let's look at what happens as x goes to infinity and as x goes to negative infinity. If x is going to infinity, that means that we're getting arbitrarily large. In the graph, that means we're moving to the right. As we move to the right, the x values get bigger and bigger and bigger. The first line is asking what happens to the y values. Well, according to this arrow, this is going to keep going down and getting smaller and smaller and smaller. It's unbounded on the low side. So as x goes to infinity, y is going to go to negative infinity because it's going to continue to shoot down. What about as x goes to negative infinity? Well, now we're extending forever and ever to the left because we want this to be unbounded on the low side. As x approaches negative infinity, we're moving to the left on this parabolic branch, and that part is going to move up forever and ever and ever. As x goes to negative infinity, y goes to infinity. And now we've marked what we call the end behavior of the graph. The previous example asked about what was happening at a specific number, but here we're asking about what happens on the ends of the graph, and so we call this end behavior. Informally, what we're saying is, on the right edge of this graph, you're going to shoot down forever and ever, and on the left edge of this graph, you're going to shoot up forever and ever. Now, I know this arrow notation can be weird, so I want to do a couple more examples, and I want to cover a couple more cases. Here we've got a graph that seems to have a discontinuity here, like we're not even allowed to plug -2 into the equation, whatever it might be. As such, that makes -2 an interesting location. So we're going to investigate what happens as x approaches -2 from the left side, and what happens as x approaches -2 from the right side. When you're approaching from the left, you're considering values that are smaller than -2, so that's this branch on the left side of -2. As we follow this branch towards x values closer and closer to -2, the graph is going to continue to shoot down. It seems to be unbounded on the low side. So y appears to be going to negative infinity. It's just going to keep shooting down forever. As we approach -2 from the right, we're considering values on this other branch that kind of looks parabolic, but not really because of the slant in it. And as we approach that x value of -2 from the right side, following this branch, the graph appears to be moving up. So as x approaches -2 from the right, y goes to positive infinity. Some of you might remember from previous courses that we call the invisible vertical line sitting here an asymptote of the graph, and what we've done is just describe the behavior of the function at that asymptote. And for those of you that have never heard that word before, well, you can giggle that it begins with ass. Let's look at this graph again and talk about end behavior, because this one's interesting. Math interesting, not actually interesting. We're going to look at what happens as x goes to infinity and as x goes to negative infinity. As x goes to infinity, we're now considering what happens on the right edge. As x gets larger and larger without bound, you're moving to the right side of the graph. Well, the right side of the graph appears to be pointing up forever and ever and ever. So as x goes to infinity, y goes to infinity. But on the left side, it's got a different kind of behavior. As x goes to negative infinity, we're going forever and ever to the left in the graph, unbounded on the low side. And this does not appear to be pointing up or down. It appears to be leveling off right at the x-axis, or at least that was my intention when I drew it. If it looks like it's leveling off a little bit below that, well, I apologize. But it looks like it's leveling off right at the axis. What is the y-coordinate of points on that axis? 0. All of those y-coordinates are 0. So the behavior appears to be that as x goes to negative infinity, y goes to 0. We call a line like this a horizontal asymptote. We'll be investigating vertical and horizontal asymptotes later on in the course. Now we have a notation to indicate what's going on at those asymptotes. Now I still haven't done an example of this third notation, so let me show you what it might look like, but it's not super interesting. I drew one more contrived graph. I didn't need to make it weird here. I just did it for fun. On the left side, we've got this line segment that kind of terminates here and meets up at the point 0,2. And then after that point, the graph continues, but kind of bouncing around or whatever. The shape of the graph doesn't really matter because what I'm asking about is behavior at 0. I want to know what happens as x approaches 0 from the left, and I want to know what happens as x approaches 0 from the right. So, as x approaches 0 from the left, we're on this linear piece. And as we get closer and closer to the point whose x-coordinate is 0, we can see that the y-coordinates are getting closer and closer to 2 because it's honing in on that point at 0, 2. And as we approach 0 from the right on this curvy piece, we also wind up at the same location. When the behavior from the left and the behavior from the right are the same, then we can talk about the two-sided behavior. Rather than asking what happens as x approaches 0 from the left or x approaches 0 from the right, we can just say that as x approaches 0, y approaches 2, and that automatically contains the original two statements. When you write as x approaches 0, y approaches 2, you're implying that that's true as x approaches 0 from the left and from the right. If it's not true for both of those, then we can't write this two-sided statement. And in our class, when you're looking at a graph, that's not particularly interesting, but this concept's going to be important in calculus. In calculus, you're going to be calling these limits, and you'll be talking about one-sided limits and two-sided limits. I'm more interested in our ability to describe what's going on at asymptotes or at breaks in the graph. When you've got a jump discontinuity, or when you've got a discontinuity with it because of an asymptote, or if the function levels off at a horizontal asymptote. Now we have a way to indicate that. If you have any questions about plotting point by point or about arrow notation, please get in touch with me. You can shoot me an email or come see me in an office hour.